In this class so far, we've spent a lot of time on algorithms for analyzing games, and very little time on the data structures that support them. In fact, the only data structure we've considered for representing normal form games is the payoff matrix. And we know that can sometimes be quite inefficient. For example, if a game is symmetric, where all of the players have identical incentives, then many of the entries in the payoff matrix are redundant. Since we know that Prisoner's Dilemma is a symmetric game, if both players choose the same action, we know they will both get the same payoff, and so we don't really need to store that payoff twice. In addition, if the players swap strategies, then we know that they swap payoffs, and so we don't need to separately store payoffs for the profile CD and DC. And so half the entries in the payoff matrix for Prisoner's Dilemma were unnecessary. And in a symmetric game with more players, the redundancy is even greater. This payoff matrix represents a 3-player, 3-action symmetric game, where if a player's choice of action is unique, they get the index of that action as their payoff. But if they choose the same action as some other player, they get minus the index of that action. And if all 3 players choose the same action, they all get 0. If we look for redundancies in this game, right away we can eliminate the profiles below the main diagonal, like we did in Prisoner's Dilemma. This entry gives payoffs for the profile where player 1 chooses 2, and players 2 and 3 choose 1. But those will be the same payoffs as for this profile, where players 1 and 3 choose 1, while player 2 chooses 2. Likewise, this profile is redundant with this one, and this profile is redundant with this one. And the same will be true in both of these submatrices. But there are also repeated profiles between these different subarrays. For example, this profile corresponds to players 1 and 2 choosing action 1, and player 3 choosing action 2, and that's just this profile repeated again. Likewise, this profile is redundant with this one. This profile is redundant with this one. This profile is redundant with this one. This profile corresponds to this one. This profile corresponds to this one. This profile corresponds to this one. And this profile is the same as this one. Plus, just like in Prisoner's Dilemma, how we didn't need to store multiple copies of the same payoff when players are choosing the same action, we can eliminate 2 of these payoffs when everybody plays action 1, and likewise when everybody plays action 2 or action 3. And in the cases where 2 of the 3 players are choosing the same action, we don't need to store that payoff twice, allowing us to eliminate all of these entries. And the end result is that instead of storing 81 payoff values in the full payoff matrix, we only need 18 payoffs to fully represent this symmetric game. And as we increase the number of players in a symmetric game, the fraction of the payoffs that are redundant is going to continue to rise. And so a new data structure to more efficiently represent symmetric games would be an enormous savings. But just deleting entries from the payoff matrix isn't really helping. What we actually need is a new data structure that will let us represent and compute with symmetric games more efficiently. And the key starting point is that we can keep track of which profiles we actually need and store the payoffs for each of those profiles. After all of our erasing, we went from 27 profiles in the asymmetric representation of the game to just 10 distinct profiles that need their payoffs stored in the symmetric game. And we can represent each of those profiles by storing how many players are choosing each action. So here we have a representation of a profile where all 3 players are choosing the first action and 0 players are choosing each of the others. That corresponds to this entry in the payoff matrix, and for that profile we can map it to the corresponding payoffs. Everybody who's playing the first action gets 0, and nobody's playing either of the other actions. This 210 vector corresponds to a profile where 2 players choose action 1 and 1 player chooses action 2, which is this entry in the payoff matrix. And corresponding to that profile, we can store that the players choosing action 1 get a payoff of -1, and the player choosing action 2 gets a payoff of 2. So this means our representation should keep track of a mapping from symmetric profiles to payoffs, where the symmetric profiles are represented as the number of players choosing each action, and we store the payoffs to each of the actions that somebody is choosing. And we could store this mapping in any of the classic data structures for dictionaries. But since the main thing that we'll be doing with this data structure is trying to compute Nash equilibria, we should also think about optimizing for efficiently computing deviation payoffs so that we can run replicator dynamics or gradient descent or any of the other algorithms that help us identify a mixed equilibrium. And that's why, in my diagram, I have squished all of these profiles together into an array whose height is the number of actions in the game, and whose width is the number of distinct symmetric profiles. Counting the number of symmetric profiles is a combinatorics problem, where we're looking at the number of ways we can assign the P players into the A buckets. And so the total number of profiles is P plus A minus 1, choose P. So this gives us 2 arrays, the first of which stores all of the profiles, and the second of which stores all of the payoffs. But we can see from the blank entries in this payoffs array that this representation still has some redundancy. Because for a profile where everyone is playing action 1, there's no payoff information we need to store for actions 2 or 3. And we can further improve our representation by eliminating that redundancy if we switch our representation away from profiles and instead to opponent configurations. The idea here is very similar. We have one array of profiles and one array of utilities, where a column in the 2 arrays corresponds. But now notice that each of the vectors within our configurations array sums to 2 instead of 3. And that's because what we are counting is how many opponents are choosing each of the actions. So this vector says that 2 opponents are choosing the first action, and none are choosing actions 2 or 3. And then we can store the payoff that the third player would get if they chose either the first or the second or the third action when the opponents are both playing action 1. And now our array of utilities has exactly 18 entries, storing only the non-redundant values from our payoff matrix. So now we need to think about how we can use these arrays to compute deviation payoffs that will then let us compute Nash equilibria. As always, a deviation payoff calculation is a sum over all of the possible outcomes of the probability of that outcome times the utility of that outcome. But Now, when we are thinking in terms of opponent configurations, the way that we calculate the probability of a configuration is slightly different. If we ask what is the probability of some opponent configuration occurring when the players are using some symmetric mixed strategy, then we need to not only multiply out the probabilities of each action being chosen, but we also need to consider the other outcomes in the payoff matrix that were redundant with the current one. To make this clearer, let's think about an example. Let's suppose that we're calculating deviation payoffs for the symmetric mixed strategy profile, where everyone is using probability 0.1 of the first action, 0.5 of the second action, and 0.4 on the third. And let's think about the probability of this opponent configuration happening when the opponents are using this mixed strategy. This configuration has one player using action 1 and one player using action 3. So we can multiply out the probabilities for action 1 being chosen and action 3 being chosen. But we also need to consider that the two opponents could be playing action 1, action 3, or action 3, action 1. So there are two different asymmetric configurations corresponding to this symmetric configuration. So we need to multiply this probability by 2. And so the probability that this configuration contributes in our summation to get the deviation payoff is 0.08. And that probability will be the same whether we're calculating the deviation payoff for action 1 or action 2 or action 3. So we can use the mixed strategy and the configuration to calculate a probability for each profile, and then we can multiply that probability by all of the corresponding utilities. And then once we've done this for all of the profiles, we can sum across the profile dimension to get a vector of deviation payoffs. The general version of this probability calculation works as follows. Multiplying out the probabilities corresponds to this product over all of the actions. For each action, we're taking its probability in the mixed strategy and raising it to the power of the corresponding element in the configuration. Because we had one player choosing action 1 in this configuration, we multiplied by that probability once. But if instead we'd been in a configuration where two players choose action 1, then we would need to multiply by 0.1 twice by raising it to this power. We multiply that out over all of the actions. Then to get the probability, we needed to multiply by 2, since there were two different asymmetric arrangements corresponding to this symmetric configuration. And in general, calculating that number of arrangements is another combinatorial problem. It corresponds to the multinomial coefficient, which is a generalization of the binomial coefficient, to the case where you're splitting things into many subsets instead of just choosing in versus out. Specifically, we have a multinomial coefficient where we are splitting up the players, but since we're looking at opponent configurations, all of these p's ought to be p minus 1. So we are splitting up p minus 1 opponents among the different actions. And so the bottom here is all of the entries in the configuration vector. So this value 2 comes from calculating the multinomial coefficient where we have 2, choose, 1, 0, 1. And in general, we calculate that multinomial coefficient as the top factorial divided by the product of all of the values on the bottom factorial. So in the case of this configuration, we have 2 factorial on the top and 1 factorial, 0 factorial, 1 factorial on the bottom, which comes out to 2. And this array representation lets us do a vectorized calculation of this product and this sum, where we will apply the same operation to each of the configurations. And it's worth rephrasing our example here to look more like the calculation we would actually do. The first step of raising the probabilities to the configurations can be done element-wise on these vectors. We'll raise this probability to this power, this probability to this power, and so on, giving us this vector. And then multiplying the elements of this vector gives us this product. But we know that we need to multiply this by the number of repetitions, which comes from the number of opponents, choose the number of players on each action for this configuration, and this comes out to 0.08. But in addition to doing this exponentiation element-wise, we could actually do this element-wise with the entire configurations array. And then we can do our product down the action's dimension and multiply them each by the number of repetitions. And that would give us a row vector with the probability of each configuration. Then, when we have the probability of each configuration, we can multiply that element-wise with the utilities so that we are weighting all of these payoffs by the probability that they happen. And then this sum is over the configurations dimension of the array, and that gives us a vector of deviation payoffs for each action. And since these steps happen every time we want to compute deviation payoffs, so that will be on each step of our equilibrium computation algorithms, we end up using the same number of repetitions for this profile every time. And so it makes sense to compute that in advance and store it in another parallel array. So this array we can compute at the start, giving us the number of repetitions for each of the configurations. And then we no longer need to perform this multinomial calculation on every step. We can just take our product over these probabilities and multiply those with this array to get the probability of every configuration by a vectorized calculation. So this data structure is a huge improvement over storing the whole payoff matrix. And in fact, it's enough of an improvement that we can represent games that are sufficiently large to cause numerical problems. For example, in this representation, it's totally plausible to store a game with 30 players and 6 actions. But the trouble is that in a game with 30 players and 6 actions, when we're calculating this multinomial, the factorials get so large that the multinomial value that we would try to compute and store is actually too big to fit in a 64-bit integer. So this data structure could handle 30 players and 6 actions, but 64-bit integers can't. So if we want to store really big games, we need to use the classic trick from probability of taking the log. If we want to do a log transform, since the log is only defined for positive numbers, we might first need to rescale our payoffs to make sure that all of the utilities are positive, and then we can apply the natural or some other base logarithm to our utilities and our repetitions. That then means that we can do all of our calculations in log space and only exponentiate at the end before the final summation. So, what does that calculation look like? Well, essentially what we're doing is replacing this probability times utility with e to the log of probability times utility. And written like this, it seems kind of silly, but the key is that when we take the log of the probabilities, we'll have numbers that are much easier to work with. First of all, note that when we take the log of a product, that's equal to the sum of the logs. So this means we would store the log of all the utilities. But then we can further break down this probability, since we know that it is a product. Before, we had the number of repetitions times the product of the probabilities raised to the configuration count. But when we take the log of the exponent, that becomes multiplication. So now we have the log of the probability times the configuration count, and the log of the product became a sum, and that gets added to the log of the repetitions. And the log of the repetitions is a dramatically smaller number than what was previously overflowing our 64-bit integers. And so we can compute this log of the multinomial and store it, which allows us to handle much larger games. And then, by doing all of these calculations in log space, and then only at the end, right before we sum over the configurations, we will do an element-wise exponentiation, getting us back to actual payoff values. So this means our data structure would store the log of the utilities and the log of the repetitions, but the configurations can stay as is. One final note is that this log of the repetitions is being added every time we compute deviation payoffs, and so we could actually make our computation slightly more efficient by just adding it in at the beginning. That would correspond in the version of the data structure I've written here to multiplying each column of the utilities by the corresponding repetitions. Or if we're storing the log, then it would be adding the log of the repetitions to each of the log utilities. And so for this game, that representation would look like this. And since we've turned the deviation payoff calculation into a bunch of operations element-wise on matrices, that's the sort of computation that GPUs are great at. And so, if we want to get fancy, we can move the computation to the GPU and calculate deviation payoffs for an entire batch of mixed strategies at once. But the overall result is that for symmetric games, rather than storing a gigantic redundant payoff matrix, we can store much more compact arrays that facilitate the deviation payoff calculation that we want to do all the time when computing Nash equilibria.